For centuries, machining meant a human operator turning metal hand wheels to dictate the path of a cutting tool. But replacing those hands with motor-driven slides allowed digital logic to command simultaneous, high-speed movements across multiple axes. The push for this automation arrived in 1947. The aerospace sector faced a severe manufacturing bottleneck. Planes and missiles required highly complex geometries, specifically the precise sweeping curves of helicopter rotor blades, which operators simply couldn't produce fast enough. Look closely at a machinist manually operating a lathe. The human brain can only synchronize 2 or 3 axes at a time. Executing continuous, multi-axis radial contouring with perfect repeatability exceeds human physical limits. To solve this, an inventor named John C. Parsons engineered a system coupling early computer equipment with a jig bore. He used these punched cards, where physical rectangular holes stored numeric coordinate data, to dictate the machine's movements. By 1952, the Massachusetts Institute of Technology took Parsons' concept and successfully demonstrated a fully modified Cincinnati Hydrotel milling machine. MIT coined a specific term for this code-driven automation: numerical control. That single modified mill evolved into an entire taxonomy of computer numerical control, or CNC, equipment. Today, the same principles drive multi-axis machining centers, turning lathes, electrical discharge machines, and water jet profilers. Yet, even with modern processors sending microsecond commands to slide motors with absolute precision, the software cannot defy physics. The physical geometry of the cutting tool clamped in the spindle remains the strict, non-negotiable limit on what toolpaths actually work. This scatterplot visualizes the core metallurgical puzzle in subtractive machining. On the y-axis, we have wear resistance, and on the x-axis, high-speed capability. Every tool selection forces a direct trade-off between these two properties. Right here in the lower middle tier is high-speed steel, or HSS. It is a cost-effective cobalt steel alloy that serves as the baseline for general metal machining. It absorbs shock well, but it cannot survive extreme cutting speeds. Moving to the upper right quadrant, we find tungsten carbide in a cobalt lattice. Carbide is significantly harder. It demands a highly rigid machine setup, but it rewards the operator with massive increases in cutting speed and feed rates. Pushing the absolute limits at the top edges are highly specialized materials. Micrograin carbide dominates precise surface finishing applications due to its tight structure, while ceramic inserts endure the extreme thermal loads of ultra-high-speed machining. Manufacturers rarely use base metals raw. They apply micro-thin chemical coatings over the tool's geometry to actively decrease friction between the cutter and the workpiece. These specific coatings perform multiple jobs simultaneously. They artificially increase the tool's surface hardness, provide built-in lubrication to assist chip flow, and act as a thermal barrier against rapid abrasion and heat corrosion. This means if a programmer writes code with aggressive feed rates, but specifies the wrong metallurgical matrix, the tool will suffer immediate thermal failure and scrap the part. The foundational tool used to execute these commands on a CNC mill is the end mill. Unlike a standard drill, an end mill has a dual capability. It utilizes its peripheral flutes to cut radially along its side, and its end-face flutes to plunge downward. However, feeding axially straight down along the z-axis requires a specific geometry, a center-cutting end mill. Its cutting edges continue all the way to the absolute center of the tool face, leaving no dead space. Contrast that with the architecture of a non-center cutting end mill. Notice the relief hole located exactly at the center of the cutting face. If you program an axial plunge with this specific geometry, the solid metal trapped under that dead space has no cutting edge to shear against. It compresses directly into the tool body until the machine physically crashes. When the goal is sheer material volume, machinists turn to roughing end mills. These feature distinct serrations ground directly into the teeth. Instead of producing one continuous curl of metal, the serrations break the material into thousands of tiny chips. This geometry drastically reduces vibration and chatter, maximizing the volumetric material removal rate. To finish complex geometry, ball end mills feature a fully hemispherical cutting face. They generate precise radiuses at the bottom of deep pockets and trace smooth 3D surface contours. But before any detailed contouring happens, the raw stock must be leveled. That is the exact role of the face mill, designed to rapidly clear large, flat top surfaces. A face mill is an indexable body that holds multiple replaceable carbide inserts. Adding more inserts to the circumference increases the number of cutting edges engaged per revolution, which directly raises the metal removal rate. The geometry of these inserts varies based on the required cutting forces. Machinists frequently use inserts with a 45-degree lead angle to distribute the load, but rely on 90-degree square shoulder inserts for right-angle step-downs. Every calculation the CAM software makes starts here. Knowing whether a tool's face allows a straight axial plunge or strictly limits you to radial contouring dictates the very first lines of G-code generated. Instead of calculating complex multi-axis tool paths to create a curve, you can use a profile cutter. These tools are physically ground to the exact inverse of the desired final geometry. This animation demonstrates the inverse kinematic relationship. When a concave milling cutter passes over the metal, it transfers its shape to generate a perfect, convex, semicircular surface contour. Similarly, a corner rounding cutter possesses teeth curved inward to form a quarter circle. One pass smoothly breaks a sharp 90-degree edge down into a precise radius. For precise non-orthogonal cuts, machinists employ specialized angle cutters, like this single angle cutter. If a part requires an undercut, like the mounting channels on the machine table itself, T-slot cutters are used. They feature profile-sharpened, staggered teeth mounted on a narrow shank to reach inside a pre-milled slot. And for extremely narrow parting off or slotting operations, metal slitting saws are deployed. They function like extremely thin side milling cutters, utilizing either plain or staggered teeth depending on the material. These profile tools act as physical hardware shortcuts. They embed the required shape directly into the tooling itself, completely bypassing the need to program complex digital contouring paths. Making a precise hole exposes a physical problem. Press a standard drill bit against a flat surface, and the center web deflects, causing the tool to violently wander off center. To stop this deflection, machinists use a spot drill. It is built with an exceptionally short flute design specifically to maximize its rigidity. The spot drill has exactly one function: plunging just deep enough to carve a precise, locating dimple in the exact coordinate of the intended hole. Looking at this split-screen diagram, you can see the mechanics. On the right, the standard twist drill tip seats perfectly into that pre-spotted dimple, forcing the flutes to track perfectly true into the workpiece without bending. This is distinct from a center drill, which is a specialized tool intended exclusively for locating the ends of cylindrical lathe stock. Notice its two-part tip. It features a small pilot drill at the bottom, which seamlessly transitions into a much wider 60-degree countersinking area. Once the primary hole is drilled, the process usually continues. You run taps to cut internal threads, feed reamers down the bore to achieve absolute dimensional sizing, or use counterbores to recess bolt heads. Generating a precision hole in subtractive manufacturing is never a single action. It is a rigid, mathematically sequenced series of specialized tool engagements. Combine these kinematic principles to get the modern subtractive sequence: a solid block of raw metal rapidly carved down into a finished, complex component. The operation begins with bulk material removal. You drop in face mills to level the planes, and drive HSS roughing end mills hard into the stock to clear the heavy stepping. Then comes the strict order of precision secondary operations. You rigid spot the coordinates, push the twist drills through the web, and run the taps to establish your mounting threads. Finally, the surfacing passes take over. Profile tools snap off the sharp edges, while carbide ball end mills trace thousands of micropasses to generate the smooth, finished contours. The software generating this motion is entirely blind. It calculates the G-code based completely on the physical tool dimensions the programmer typed into the interface. And physics always wins. The highest speed spindle on the market cannot save a program that commands a non-center cutting end mill to plunge straight down. It will simply shatter the tool. Subtractive precision is realized at the spindle tip. While G-code provides the instructions, the final outcome depends entirely on the metallurgical and kinematic realities of the...
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.